well, the last unit before the exam. And you can see the dates for everything. I don't really feel like we're rushed here, actually. This is a short unit. It's a pretty simple unit. It's not too tough. In fact, these are words you've probably heard of before, impulses and momentums. So it's not that difficult. But you can kind of see the deadline, or the deadline we're kind of up against. May 9th is when I'm planning on the test. And I'm actually telling you kind of when the pop quizzes are. That's my scheduling. Okay, so I have a question for you. Are all forces created alike? In other words, is this force here that I'm pushing with, is that the same as that force?
No.
Well, it might be, right? It might be the same force as so many newtons, but do they have the same results?
No.
No. Why is that?
Momentum. Impulse.
Change in momentum.
How about not use words we don't know definitions for? What do you see? What's different between
You
the
push
two?
this one longer.
Yeah, so it's a different amount of time, right? So maybe there's some kind of effect of time with force that might cause something we're seeing here. So anyway, I have a question. First of all, let me show you the lab setup, the demo that I'm going to be doing here. I have the cart. By the way, you're going to use these later on when we do one of the labs. But it has this, this plunger on the back side of it. I'm going to leave it out like this. And it's going to be hitting the force probe over here. I also have a motion detector that's going to be measuring the velocity. And so I'm going to kind of roll it like this, and it's going to collide with the force probe. I want you to talk to your neighbor. How would you describe this motion here in the beginning before it hits? Talk to your neighbor.
Angular momentum.
What do you guys think?
What about the velocity?
How would you describe the motion before it hits the...
Constant velocity.
Well, if you take air resistance.
Yeah.
Okay, so if you take air resistance and anything else?
It looks pretty
If
complicated.
you take air resistance out and anything else?
Friction.
And friction out, what would you say about the motion?
Constant.
It's constant. And let's say there is no air resistance, which is a pretty good approximation because it's not moving fast. Is it a pretty good approximation to say this is a frictionless crack?
Yes.
Yeah, that's why we spent $3,000 in the tracker show.
Nuh-uh.
At least $2,000 for one of these.
But that,
That's like a car.
A junkie car. So anyway, they are pretty, those are pretty good assumptions. I want you to kind of sketch on a piece of paper somewhere what you think the graph, the velocity time graph would look like for this object here right before it collides. Kind of sketch it on. So it's going to be a velocity versus time graph, kind of sketch the motion.
That's what I had.
Okay, I got to move, so I'm going to assume you've done that because that's pretty quick, right? Okay, the next thing, I would like you to sketch continue that velocity time graph on in time. So you're going to add to that graph what it would look like after it collides. So it's going to be moving back this way. It's going to bounce off. Okay. So in other words, I'm not talking about the collision. I'm talking about before the collision and after the collision. You describe the motion on that velocity time graph. And then show it to your neighbors.
Because the opposite directions. Maybe it'll be
Okay, now what I'd like you to do is try to figure out what the velocity versus time graph looks like right in the region where it's colliding, actual physical contact. So finish your velocity time sketch. Probably. You're guessing that it's going to look like. Okay, lastly, we're going to be looking at two graphs here. We're going to be looking at a velocity time graph right up here, and we're also going to be looking at a force time graph. Could you sketch what you think the force time graph would look like for? We're looking at the force that this thing senses.
It'd be nothing, and then it'd be really high.
Do Do you have something drawn so you can at least compare it and see if it matches? Okay, so are we ready? Okay, let's actually try it.
Momentum graph.
Wait.
Oh,
No.
oh.
Do it again. All right. So is it similar to what you thought for the velocity time graph?
Yes.
No. Is it similar to what you thought for the force time graph?
Very.
Similar?
Sort of.
Okay. So explain what's going on here. Constant velocity, and what kind of velocity is that?
Positive.
It's positive. And then what's this velocity here?
Negative.
It's negative constant
Velocity
velocity,
is
right? And then here, what's happening? What is it experiencing? It's
Accelerate.
an acceleration, right? Because of an outside force.
Yes.
Okay. So, which direction is the force on the car?
Negative.
In the negative direction.
That's right.
Does that make sense?
Yes.
Okay. So, what do you think, how would it change if the thing's going slower? What would change about this graph?
It's small.
It's smaller this way, you mean?
Yes, and smaller the other way.
What about this graph? How would that change?
Price,
Be
smaller.
smaller. Be smaller? What do you think would change if I were to put a mass on here?
Nothing. Nothing, because I don't really know. I think the force.
The force would be
Want to try it?
Yeah, let's do it.
I'm hoping it doesn't.
Keep the displacement.
Anti-differentiation.
Momentum.
Oh, look at that bigger force. Was it
looks like a
heartbeat?
It's weird. Try again.
It do.
Close enough. Now, of course, that's going slower. Does it look kind of the same?
Yes.
It kind of has the same look to it. Now, the numbers must be different.
It's not.
Okay, now, I want to look at things for a second here. That was slow. I'm going to go a little faster than that. What do you notice about when that force occurs in time?
right when it is
Relative.
Right when it's changing direction, right? So I want to look at the units. I want to see if there's a relationship between this graph and this graph. And sometimes looking at the units can help. Let's start down here with this graph here. This is force versus time.
Newton's over second.
Well, that could be one thing. I can find the slope, right? Newtons over seconds. What's another thing you can find for graphs?
Like the area?
The area. How would you find the area? Think of a calculus term. I can integrate. Watch this. This is cool. I'm going to integrate right in here. There's something called integrate. And it's going to find the area of that. And the area is negative 0.5198 newtons times seconds. Does the units seem to make sense for the area? Newtons times second. Is that energy?
No.
No, what's energy? Newtons times meters. Let's look at the units here. What is a newton? Kilograms times meters per second squared times seconds. It cancels out that second, and so I have kilograms times meters per second. That's not energy, but look at that. What is kilograms? That's mass, and what's meters per second? Do you think there's any relationship between this graph and this graph, which has units of meters per second? What other thing would I need to know? Mass of what?
Car.
The car. I want to do a really quick calculation here. The mass of the car is about, I've already massed it for you, I'm sorry, we're running out of time, so I'm going to do it myself, is about 0.5 kilograms. About. Okay? And the velocity, I'm going to find the velocity right up here and the velocity right here to see what that is. because that's where it's kind of colliding. So I'm going to pick the same area, hopefully, about the same. And I'm going to find the maximum speed and the minimum speed. The maximum speed is 0.4991 meters per second. That's up here. And the minimum speed is negative 0.4219 meters per second. If you take 0.5, I expect you guys have calculators out, right? You need to do a calculator. Can you try to see if you can get this number here from those numbers? Right, because those are velocities, those are speeds, and this is the mass. That's what you guys said. You said somehow maybe these three things here are related here. Everybody's got their calculator out and everybody's trying. They're trying their different permutations on this.
I can't afford it.
When somebody gets something that's close, you need to share it with your neighbor and show them how you got it. In other words, if I take 0.5 times 0.4991, that doesn't give me this. That gives me positive 0.24 or something. If I do 0.5 times negative 0.4219, that doesn't give me this. That gives me negative 0.21 something. Is there any combination I can do with those to give me this? Oh,
We will, hold on. The master physics is,
everybody's trying a different permutation, trying to see if there's something that's close to that.
I did my sister's
Now let's try to use our brains here, because it seems like people aren't getting it.
Wait.
No, wait a second. Oh, we have something.
Yeah. Oh, look, I already got that.
Oh, okay.
That's not that close.
It's really close.
I think really.
What'd you get? If you got something fairly close, share it.
We got 0.59.
Yeah. Is it positive or negative?
Negative.
Negative? Well, how'd you get it? What'd you have to do?
We just divided the two velocities and then multiplied by the.
Whoa, wait a second. Divide the velocity. What happened to the units?
They cancel.
That's not good, because we want kilograms times meters per second, right?
Ooh.
She will never be.
0.5.
Whoa, listen. What? Say it.
You can do 0.5 times the 0.4991 and then divide it by the other ones.
No, wait a second. When I do that, it's going to cancel out the units.
Darn.
Yes.
Here, add the two velocities, absolute value both of that, and multiply by 0.5, you get 3.
But then they give me a positive?
Well,
I have a question for you. Try this. I need to get a negative number, right? What if we did this number times this number, because it's already negative, minus this number times that number? Would that give me a negative? Did you guys listen? This number times this number would give me negative, right?
Yes.
If I did minus this number times this number, would that give me more of a negative number?
Yeah.
Yeah, it would.
What do you get when you do that?
Probably that.
0.46.
What'd you get?
Negative 0.46.
Negative 0.46. And that would be kilograms times meters per second. I mean, it's not perfect, but it's pretty close. I mean, it's better than what I've heard from anybody else. And it doesn't cancel out the units, right? So let's see if we can come up with some kind of relationship for that. The area underneath this force time graph, oh my gosh, I don't want to have to say the area underneath the force time graph every time. I need to invent a word.
Momentum.
Let's call it impulse.
No.
No.
Okay, so the area impulse. Impulse equals area under force time graph. It's kind of right. I mean, when I was pushing on that chair, I was kind of giving it an impulse. I had an impulse to push that chair. Yeah, that worked.
yeah.
Okay, impulse. The impulse which is the area under the force time graph, that appears to be, so that would be the force times the time, or the integral of that. That appears to be equal to the mass times, which velocity was this one? Initial or final velocity? Final velocity. Minus the mass times the initial velocity, isn't it? So I have a mass times a integral of force times delta t is equal to a mass times a change in velocity. I don't want to have to say that every time either. How about we define mass times velocity? Let's just call it something. Let's call it momentum.
What?
Oh.
Hey, we're way ahead of you. I don't know, I don't like that. Yeah, how would we make up a better word, a shorter word?
No. We only have 7 minutes, guys. We only have 7 minutes. Bear with me.
Deceleration?
So the area under the force time graph, impulse, is equal to a change in, what is this new term I just came up with? Momentum. The impulse is equal to the change in momentum. Question for you. Is the impulse, new word, equal to momentum? No, it's equal to the change in momentum. Okay, hopefully you guys have these numbers down because I'm getting ready to erase them. They kind of go along with your lab.
Okay.
I'm going to show you why this unit is pretty fast, because the truth is you should kind of know this stuff already, except now I'm giving you new words. Impulse, momentum. If I start with F equals ma, what is A? What is acceleration defined as? Yeah, it's a change in velocity per unit time, right? Per unit time. What if I multiply both sides by delta t? Is that the same thing as this?
What?
So really, this stuff that we're doing is stuff we kind of know already. We're just giving it new names. It's kind of like we're rearranging the mathematical models for solving for a different variable and calling it different. Can you see why this unit is kind of fast? This is also a good place where we can start practicing some calculus, though, since we know it already. We already know this F equals ma kind of stuff. Because what this means is, if I can rewrite it, the symbol I'm going to use for momentum, something else you need to know, is this. I have a little bit of time left. And one more thing you need to know, the symbol we're going to use for momentum is E. The reason is a historical reason, is one of the first scientists to study this, Leibniz actually, one of the inventors of calculus. He called this progress, the progress of an object. Sometimes this is thought of as inertia in motion, momentum. This is another way to write then this impulse equals change in momentum, and that means that the force is equal to the change in momentum over the change in time. What would be a calculus way to write that? This is uppercase delta, what's lowercase delta? Yeah. So it's the derivative of momentum. So if you know what momentum is with respect to time, so in other words, let's say momentum was equal to 3t, what would momentum, or what would force be equal to?
3.
Just 3, yeah. Okay, so you have a lab response at the very end of the packet there. That's something you need to work on.